Let's talk about communication networks. This is a block diagram. This would be from early 2000s. In this case, you can see we've got 1, 2, 3, 4, 5, 6, 7 modules on the network. Our data link connector is always going to be present. That's where the scan tool plugs in and becomes one of the computers on the network, so it can speak with the other ones, get codes, live data, control outputs. Here's a network from, this would be around 2012, 2015, for just like a standard vehicle. In this case, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 modules on this one. So things are getting busy. Our data link connector is yet again present so that we can, with the scan tool, monitor and speak with modules on these 3 different networks. And then this would be 2017 to present. This would be, it's becoming more common on just like standard equipment vehicles, but this originally was on more luxury vehicles because of the added number of modules. I've got 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 22, 24, 26, 28, 29, 30 modules in this case. So continuing to get busier and busier. And I have 1, 2, 3, 4 networks on this one. And right off the bat, you can see that now my data link connector is part of the 31st module. This is its own module all by itself. We're limited in this case. Each module can hold around a maximum of 12 modules on it. They try to keep it just under 12 if possible, but if we start to get too many modules on this network, the constant chatter becomes too much, and it's just like being in a room full of people all having different conversations. It starts to become difficult to even listening to the conversation that you're having. So that's what we're seeing here is as we add more modules and more electrification to vehicles, well, then we also need to add more networks so that these modules can have conversations that are meaningful with each other, I guess, for lack of a better word. So we've seen this image before, speaking about what the real benefit to having modules in the first place, and then module communication in a vehicle. In a fully conventional electrical circuit, each circuit needs its own control device, so a switch of some sort or maybe a sensor. And then that directly controls each of the outputs. So if I want my window to roll up, I got to push a switch and hold it until I don't want it to roll up anymore. If I want my lights to turn on, I got to turn the switch on when I want them to turn on. You can see where I'm going with all this. For a module controlled and multiplexed, or modules on a communication network, well then all of a sudden I can have something like a switch that's in the door for the latch, and when I open the door, a signal gets sent to turn on the interior light. Exterior lights may come on as well, what we call puddle lights, so that we can see around the vehicle as we're trying to get the family out of it and stuff. We might also want a light to come on in the instrument cluster on the dashboard to let us know that a door is open, right? We also might want it to be attached to an alarm system, so if the door opens when I've locked the vehicle with my key fob, that it honks the horn and does all this. So you can see how now all of a sudden one switch can have many different outcomes depending on the environment or the circumstances that the computers find themselves in, versus in a fully electrical circuit, that one switch can really only accomplish one job. So we're just trying to add features without adding more exorbitant weight and cost to a vehicle. And complexity, it'd be much harder to diagnose that way. Here's a GM block diagram of a network. Again, our DLC, data link connector, is in full view. The scan tool is just another computer that hooks up to that, and I think they do a pretty nice job showing that there. Then I have my twisted pair of wires that runs to all the different modules on that network. Now the modules are all sending messages back and forth. Some of them are paying attention to all the information, and some of them are just cherry picking some of the ripe stuff that they care about. And in that image, it showed that the wires are a twisted pair, and the reasoning for that is that a twisted pair of wire is resistant to radio frequency interference. So those are electromagnetic pulses that come down from radio towers that we pick up and listen to in our car. Our cell phones produce radio frequency. When we go by like a high tension power station, though, that's producing a lot of electromagnetism as it's converting high voltage down to lower voltage through all those giant transformers. And even just things like this cable could be going to a power window or maybe the starter motor. And you can remember when we measured the current flow to the starter motors, we used an inductive amp clamp that clamped around the wire, and it picked up the magnetism created by current flow. And that magnetism could interfere with the little Morse code signals that the modules are sending each other, because the modules aren't really producing any current flow. They're just trying to pull voltage up and pull voltage down to make this like mirrored Morse code message that it sends out. So we're not really trying to actually flow current, we're just trying to augment how much voltage is on a wire. And so that's pretty easy to mess with. And so things like twisting the wires, and we'll talk about terminating resistors as well, try to help give us a little bit more robustness to the circuit so that we're not constantly having issues. All right, so let's look at the simplest of our networks and the simplest of the simplest of our systems and the simplest network on that system, which is the ISO. International Standards Organization. It's just engineering stuff. This ISO network, in this case, goes to the restraints control module and the parking aid module, and it's just a one-wire network. These modules don't talk to anybody else except for when we plug a scan tool into the data link connector, and the scan tool can then retrieve codes and look at live data through those modules. Apparently the airbag module and the parking aid, this is like the beeps when you're backing up, they don't need to know information from anywhere else. They produce enough and have enough sensors that they are able to work by themselves on this vehicle. Medium speed network, that's up here at the top. So the medium speed CAN is slow in the grand scheme of things. It's not super slow, but slow, and it's going to be mostly our body electrical stuff. So you can see Smart Junction Box, which is like a body control module, so lighting, horns, locks, power windows, radio, that kind of stuff is controlled through here. And then the instrument cluster, which is our gauges up on the dashboard. And you can see the connection to the data link connector, CAN high, CAN low. Then our high-speed network, so yet another twisted pair of wires. These operate at a much higher rate, and the modules that we need to be able to think more quickly are going to be on this network. So the PCM needs to be able to control fuel injection, which a fuel injector fires for about 1 millisecond to 1.5 milliseconds. Is the entire firing duration of the event. So that module needs to think quickly. ABS, if I'm sliding off the side of the road, I would like that module to be able to make as many changes and adjustments as possible to help keep me in the direction I was trying to head. And then on this 4x4 module, you can see the little dash line around it. That just means it's optional. So this is pulled out of Escape. So they have the option of being just front wheel drive or being all wheel drive. So that would be the difference between whether or not this module is equipped on the vehicle. Now, as far as speeds go, There's a clock inside of every computer, all the way down to a clock has a clock inside of it. You know how some clocks run a little fast and some clocks run a little slow? Well, it just has to do with the quality of the semiconductor material that makes the clock. So a clock is really just a crystal, a piezoelectric device that when we send current through it, it vibrates at a frequency. The more refined that crystal is, so it's just the semiconductor material that we're looking for, the more consistent that frequency is. When we get something that's not quite at a high purity, it might work a little bit faster if it has conductors inside of it that wouldn't normally be there, or maybe a little bit slower if it has insulators inside of it. So that clock just sits there and vibrates, just like the old Viking ships, the guy beating the drum for the people to row. Well, each one of those beats is a chance for a 1 or a 0 command to happen. And so the faster that those beats happen, the faster the computers can think, and the slower they happen, the slower the computers can think. On the MS-CAN side, things are moving a little bit slower because as humans, our brains can't really intuit things that are broken up into fractions of a second. Excuse me. Like old movies were 24 frames per second. So 24 pictures in a second made our brains think that there was a continuously moving image being shown to us instead of 24 separate ones. So if it takes an extra few milliseconds for my power window to roll down or for the headlights to turn on, well, whoop-de-doo, it's not really going to make a big difference to me. For the PCM, however, if it takes an extra couple milliseconds to open up that fuel injector, well, the timing may have already passed. Think about how fast a crankshaft is moving and how quickly valves open and close. If it's trying to open the fuel injector at the right time, but we've got a window of a few milliseconds on either side of it, well, we've just kind of ruined the entire thing as far as drivability goes, and emissions are completely out the window at that point. Along with the twisted wires, our networks are going to have termination resistors built into it. So they call it network termination. It's not like killing the network, but the point of these resistors, which are 120 ohms each, is one, if the modules are pulling voltage high and low, we need something that's actually going to drop the voltage and return us back to like a normal state. So they're there for that, like a shock absorber more or less. They're also there to help eliminate the magnetic interference that can go from all the other circuitry in our vehicle, much less all the radio frequencies and stuff that we come across just by driving around in the world. So these resistors are there as a way to make the system much more robust. It almost makes it have more mass, if you think about that. Like, it's pretty easy to push like a feather out of the way, but if you tape that feather to a boulder, well, then all of a sudden it's a lot harder to do with it what you want. That's what these resistors are up to. Each one's 120 ohms, and you can see if I'm coming out, let's say I'm just coming out my high side of the circuit, I have two pathways to return to the low side, so they're in parallel with each other. So if we think about our parallel math, well, I need to do 1 over my first leg's resistance, so 1 over 120, plus 1 over the second one, so 1 over 120, which gives me 2 over 120. I have to take the reciprocal, flip that over, so 120 over 2. Well, 2 goes into 120 60 times, so my total circuit resistance is 60 ohms. If I took the battery off, or disconnected the battery, and went right through the DLC, if I found the 2 pins in that were for the medium speed CAN, and I use my ohm meter, I should be seeing 60 ohms on this vehicle. Like I said, this is an escape, so Ford has decided 120 for each of those resistors, but all manufacturers are somewhere in that range, 100 to 120 to maybe 140 in some cases. But like I said, when you do this test, you're going to be pretty close, and you should also be able to find the information in service publications as well. The use of doing this ohms test is if I had an open and one of my wires or one of my resistors is burned up, I'm going to see that 120 ohms. So I'm going to know, oh, I've got an open somewhere that I need to diagnose. If my wires are shorted together, like they got pinched because a dashboard got reinstalled and the harness was in the wrong spot or something, I'm going to get less than 60 ohms, probably somewhere pretty close to 0 ohms. So now I know, oh, I'm looking for a harness that's damaged and the wires are chafed and pinched, touching one another, right? So it doesn't diagnose the issue for you, but it does give you a fair amount of information so you can start heading in the right direction. Gateway modules. Every vehicle is going to have a gateway module between at least two of its networks. All networks are going to need to be able to communicate messages from one to another. And the reason for that is something as simple as like our speed sensitive volume. So my ABS module is monitoring wheel speed. You can tell I'm going 27, 28, 29, 30, 31 miles per hour. Well, what might need to know that? The radio, because as we go faster and faster, if you have a radio with speed sensitive volume on it, it's going to raise the volume of the radio to combat road noise so that it seems like it's the same volume to us, even though basically everything around us has just gotten louder at the same rate. The module in this diagram that can jump between the two networks is the instrument cluster, because it's on both the high speed and the medium speed. So it takes these high speed communications and slows them down to a rate at which the smart junction box can understand them. So it doesn't sound like Alvin and the Chipmunks after they had a couple cups of coffee. And vice versa, if there was information from my smart junction box that I would like to see on my high-speed network, it would speed those messages up. So it has that added feature built into it, which is pretty cool. This is just showing a chart of some different faults and failures, which ALLDATA would have this in there for almost every vehicle you could think of. And just shows that on an ISO circuit, because it's only one wire, if there's any kind of a fault, no communication is the symptom. So it just wipes it all out. On our MS CAN and high-speed CAN networks, you can see that these are mirror images of each other, right? 4, no communication, 3, yes, 2, no. Same thing here. What happens is the network sticks around average of 2.5 volts. So if we turn the key on and just stuck our meter into the data link connector and measured voltage, we'd come up with an averaged voltage, because our meter can't keep up with the time frame at which our modules can talk to each other. It just averages the stuff out. We'd see somewhere around 2.5 volts. It'd probably be fluctuating slightly as the different messages came by, but that'd be something that we could do to see if our network's working at all without even having to hook up a scan tool to it, which can be convenient. And because we have two wires, and we're going to get into this in depth, but because we have two wires, the network can still work properly, well, somewhat close to properly, in the event of certain failures, like a CAN low short to ground, CAN high or CAN low open. We still have that other wire that's going to send the information. We're going to look at this in a little bit more depth once we have the oscilloscope snapshots in front of us, because it makes a little bit more sense once you can see how the voltage actually reacts. Another little graph showing whether or not a module is a terminating module. We know for the vehicle we've been looking at, instrument cluster is a gateway module, which is nice. It shows us that. Well, what networks it's on, and yes, it is terminating. This also shows us that we have a few optional equipment modules. So if we try to pull codes out of the 4x4 module and it says no communication, well, that might just be because it's a two-wheel drive vehicle and there's no such thing as a 4x4 module on that vehicle. Here's a look at that again, and you can see the little dash lines showing us optional. All right, here is our more modern diagram. So this is looking at like 2015-ish, somewhere around that range. high speed, medium speed, and now we have this infotainment ICANN. So the way that these modules communicate with each other is through a method called multiplexing. So they don't have an order in which they all sound off every minute or every second or something like that. They just send out the information as it becomes available. And the way that it works is that multiple messages might be sent out at the exact same time. So that's like being in a room with multiple groups of people having different conversations. So if you're having a conversation with your friend and you're focused on your friend and you're going back and forth, there's a good chance, even though there's other stuff going on around you, you can carry on the same conversation. You're not picking up what other people are speaking of necessarily, right? You're focused on what you're doing, but those other conversations are happening as well. The issue can come up when there are too many modules having conversations at the same time. That's being in an overcrowded room, and that's why they keep adding more networks so that we don't get to the point where we get so overcrowded that the modules can't pay attention to each other anymore. Network termination again, and you can see we've got all these different networks. And my IPC is a gateway module between the ICANN and medium speed, and that's one of the termination networks in the ICANN, as well with the audio control module. The IPC and the body control module are terminating networks for the medium speed CAN. And then the body control module and the PCM are the terminating modules for the high speed CAN. And you can see these are all still hardwired right into the data link connector, which makes our lives much easier as technicians. Here's what a wiring diagram instead of a block diagram looks like. Here's my data link connector. And if we look, 6 and 14, these are the pin out numbers on the data link connector. These are always going to be a communication network. And so 6, if we follow that, I'm just going to the first one I can find. That's our high-speed CAN high wire. 14, high-speed low. You can see there's a splice off of that one. Goes up to my 4x4 module for low. And there's my high right here for the 4x4 module, these splices. And so this shows you how these communication packets are being sent at the same time. Like this is talking and it's spliced to the same wires that this is on, and this is talking and that's spliced to the same wires that this is on and this is talking. So there's just a whole bunch of chatter going back and forth. And the packets themselves make it so that the right information makes it to the right module, and even has the right priority, right? Like if I'm sliding and having a traction control event, that's way more important than knowing what the temperature is outside, right? I agree. Here are broadcast messages. So let's say that ABS module has a traction control event going on. Well, the ABS module is the one that knows it because it's looking at wheel speed sensors. That's how it determines whether or not that's happening. We got wheels that are slipping. It's on the HS CAN. And the modules that care are the instrument cluster and the powertrain control module. Instrument cluster is going to show like a little symbol flash and letting the driver know, oh yeah, that's why the car's acting funny, is because the traction control is working. PCM wants to know because it's going to start to kill fuel injectors, maybe retard ignition timing, trying to pull torque out of the engine so we're less likely to be slipping. And the ABS module sitting there pumping brakes and doing all kinds of crazy stuff trying to get us to have the traction that we're supposed to have. So a little snapshot at how the engineers put this stuff together. This is our most modern of the diagrams. I've got 1, 2, 3 CAN networks, high speed, and 1 medium speed network. And now that we're into the realm of having 4 different networks, we've overfilled our data link connector to the point at which we need to have this gateway module. So this is a good time to take a little walk down memory lane and talk about the history of the data link connector. Before 1996, auto manufacturers were allowed to put whatever diagnostic port on a vehicle they wanted to. It could be anywhere on the vehicle. Remember, Isuzu was pretty famous for having them in the glove box. Volvo had it underneath the hood of the vehicle. Ford had it underneath the dashboard somewhere. Sometimes it was on the passenger side, sometimes it was on the driver's side. So even just like trying to find the right diagnostic port could take some time, much less finding the right adapter for your scan tool, hoping that you had the right adapter for your scan tool. It was just like a whole huge proprietary mess. Independent shops were starting to really struggle with this stuff because this is around the time that emissions compliance was really starting to take hold. The Clean Air Act was old history at that point, and the manufacturers were being expected by the government to produce vehicles that met emission standards. And so more codes were possible to, just like as far as things that could break on a vehicle as we were adding all these devices, more stuff could happen, but the average tech that wasn't working for, a dealership had less and less or fewer and fewer tools to be able to diagnose these issues. And the tools they did have only worked with one vehicle, and they might have a GM in and then a Toyota and then a Volkswagen, right? Becomes really complicated, very expensive, and really time consuming. So when OBD2 came out, Onboard Diagnostic 2, this was the government responding to the cries of the independent world, saying look, this is a bunch of baloney. You guys are being proprietary just because you don't want the independent shops to be able to work on your vehicles, and it's like an antitrust issue, right? It's these companies trying to get a monopoly on auto repair. So they mandated data link connector needs to look like this. It has to be in the footwell of the driver's side front of the vehicle, so it's easy to find. You go to Walmart, buy a scan tool, it plugs into a Lamborghini just like it does into a Honda, and the information you can get out of it is going to be consistent as well. When we get into things like traction control and transmissions and like radios, that's all proprietary still, and there's other types of legislation that have happened about that. OBD2 is really focused on emissions, and so there are a bunch of codes that are government mandated, like a P0300 means that you have a misfire. It doesn't know what cylinder is misfiring, but it's telling you got a misfire bulb. And so you can come into any car sold in the United States, plug in that scan tool, and if the car is missing, you should be able to get a misfire code out of it. Because of that, we're limited to the size and shape of the data link connector because that same scan tool has to plug into everything. So we only have 16 slots for wires to go into. And when we have 4 communication networks, that takes up half of the slots all by itself. And some of those slots are meant for other things than just communication networks. So long story short, what's happened is there's this gateway module that now acts as a gatekeeper for the scan tool, so it can translate information from the medium speed CAN or high speed CAN 3 to the data link connector so that we can pick up the information and actually pull codes and look at live data and try to diagnose what might be going wrong with a radio or a auto opening tailgate. Who knows, right? So the high speed 1 and 2, at least in this iteration, because we still had enough room in the data link connector for 2 networks no matter what, high speed 1 and 2 are hardwired, so that acts as normal. And all of our high speed networks are going to operate at 500 kilobytes per second, which is pretty fast, right? We're thinking about that clock. So that clock is capable of 500,000 pieces of information every second. It's pretty substantial, I would say, right? When we get over to our medium speed network, here we are. we come down to 125 kilobytes per second. So that's almost a quarter, right? Maybe closer to a third, but much slower than what our high-speed network is actuating at. And our medium speed and high speed CAN 3, they're not hardwired. The gateway module is translating for those networks. This is a little look at what it looks like inside that gateway module. High speed 1, hardwired. High speed 2, hardwired. And then we have these little microprocessors, computers. And these are translating the information. One, it receives the information, so it could gateway that message onto another module in the network, or if we have the scan tool hooked up, it can send it over onto the HS2 CAN so that we can pick that information up with our scan tool. Multiplex messages, and this is just a quick look, something that you can play around with, and when we do the lab activity you'll see a bunch of this stuff as well. Just like, you know, again, let's pick on ABS. ABS is active, ABS puts out the message, in this case it's on HSCAN2, and now all of a sudden there are all of these modules that care about it. Restraints control module, this is our airbag module. It has little accelerometers inside of it, so it helps the car know, like, is it sliding sideways or is it going straight ahead like it's supposed to be doing, right? Are we starting to spin? Is there a tilt going on? We can tell all that kind of stuff. We have our power steering control module. So power steering, you know, do we want to maybe help steer the vehicle because we have electronic power steering systems now? Do we want to make it so that the steering is harder so that the customer can't overcorrect? The vehicle dynamics module goes along with some more of those accelerometers, the gateway modules at our data link connector, and I believe that this is our column control module, so this would be like up at the steering wheel. Just a bunch of bits of information that they're picking up these little bits and doing their part to help inform the customer and then also keep us pointed in the direction that we want to. That's probably what the cluster control module is for, is it knows which way we got the steering wheel pointed, and it knows from like vehicle dynamics and restraints control what way the vehicle's actually going, and it's trying to line those two things up with each other. Data link connectors out of 2 random vehicles that we have out in the shop. I highlighted 6 and 14, 11 and 3, because these are going to be communication terminals. So if we look at 6 and 14, 6 high speed high, 14 high speed low. On this one, 6 high speed high, 14 high speed low. Then we have other things like 16 is always power, fuse 15, circuit breaker, 16 fuse or circuit breaker. 4 and 5 are always ground, ground on 5, ground on 4, ground, ground. So there are some things that are always consistent, like this 16 and 4 actually power and ground the part of the scan tool that communicates with the network, because it needs to be on the same electrical circuit as everything else, basically on the same battery as everything else, so that it has the same reference and stuff like that. But just trying to make it clear that there's that standardization. All right, so now is the time, if you want to pause this or whatever, let your brain cool down. We're going to look at the, excuse me, lots of talking. We're going to look at the actual waveform captured by an oscilloscope of an active communication network. So this is a high-speed network. We have our y-axis is voltage, and you can see we're up in positive voltage. Our average is around that 2.5 volts like we talked about before. My x-axis is time, and it's very hard to see, but that says 20 microseconds. There's like a weird little m called a mu in there. 20 microseconds, and that's each one of these divisions is 20 microseconds, is 0.00002 seconds. So this is happening incredibly quickly, right? I said this is our high speed. And what we can see is that our high side pulls high, so we go from 2.5 up near 3.5. We have a little termination spike at the end that comes up close to 4. Low side starts at 2.5, drops down around 1 3/4ish, I guess in this case. The spike goes down closer to 1.5. But you can see that there's this carbon copy or mirror image of the information, and that gives us this robust nature to the network. If part of this gets chopped off for some reason, we still have the low side that has the same information in it. It's just a carbon copy. The network message is broken up into, the originating module and who it's really intended for, the priority of the module, the actual communication, the data itself, a way to reconcile the data to make sure the information it received makes any sense, and then this termination spike, just like an over and out. We're done talking for right now. If we have any issues with these packets, a U code will be set. In our vehicles, we have P codes. So that's usually powertrain related, so engine, transmission. Then we have our C codes, which are chassis. So that's going to be codes like our ABS. If we have air ride suspension, four-wheel drive would set chassis codes. We have B codes, body codes. So that's going to be like my radio is broken, my lights don't work properly. And then U codes. They used to be called undefined. It was just like the catch-all for random codes that didn't really quite fit into the other categories. But now, over the last 10 years especially, U codes have become our communication codes. And these are codes that set when, let's say, my ABS module breaks or it loses power or something like that, and it no longer sends out information. There will be a bunch of modules on the high-speed network that would say invalid data received from the ABS module, or no communication with ABS module. That is a good module that has responded to the scan tool saying, hey, look over there, the ABS module doesn't seem to be responding. That's not normal. It's not saying I'm incapable of receiving the information. No, it's not saying that. It's saying I'm not receiving it from there. And you'll see it in a bunch of places, and it's all just these modules pointing and being like, take a look at that guy. It doesn't seem to be doing very well. All right, normal waveform right here. This is what we should see. On a medium speed network, it'd be a little blockier, maybe spaced out a little bit because it's slower, but it would look very similar. So now we have a failure. The two network wires are shorted together. No communication, we're stuck at 2.5 volts. CAN positive shorted to ground. No communication, we're stuck at 0 volts. And we get these little spikes that just show the system trying to wake back up and try and maybe start to communicate, and then it senses this short to ground and it shuts itself off to protect itself. CAN low shorted to ground. This is the first failure we've seen that we could still have some communication. And what you see is we still get this blocky look. Like if I go back to what it should look like, see the little rectangles basically. This just looks like a Hall of Mirrors version of the same thing. It's all distorted, stretched out. So that's why they're saying it might be degraded. But the way that these modules really pay attention to the information is, in this case, we're waiting for voltage to rise up past a point, I believe, because it looks like our low side stays down around 0 the whole time. But we look for voltage to rise up past a point, and then it uses its little clock to count. Okay, so it rose up past, let's call it 2 3/4 of a volt, rose up past it. How long does it take for it to rise up past it again, right? Obviously it has to fall, but it's not paying attention to that. Falls, comes back up. Oh, it was 18 microseconds between those two rise past events. Let me look at my little chart. Oh, that means blah, blah, blah. Okay. And what's happening is the different time lengths mean different bits of information. We're taking a bit, think of it like a letter in the alphabet, and turning it into a byte, think about a word, and then we're turning that into a phrase, right? Think about a phrase. And then that gets turned into a programming sentence and then a big paragraph from there. So we're just adding these ones and zeros more or less into bigger and more complex messages. CAN positive, shorted to battery voltage. Again, communication may continue at a degraded level, but you can see that it's drawn our voltage way up near battery voltage. So we would definitely know by either using our multimeter or an oscilloscope that something is shorted to power, since we're supposed to be averaging around 2.5 volts. CAN low shorted to battery voltage kills it. That's another short circuit, right, which is bad news. We got battery voltage shorted to what's basically a ground. And so it gets all mad and it shuts communication down so it doesn't wipe everything out. And then this CAN circuit signal corruption is, let's say I went through a big puddle and my ABS module is now full of water. Short circuits are happening. Even if it's trying to communicate, the information that's coming out of it is non-decipherable. This is that sawtooth pattern that they're referring to. This is a sign of like a capacitor discharging. But this module is all messed up and it's just screaming on the network to the point where other modules can't get their messages through. So we might get some information through. We might have multiple weird communication failure codes. The way that we'd most easily diagnose this is once we started the diagnostic, we would start then unplugging modules one at a time until things started working properly. And then we would start plugging them back in again one at a time until we figured out which one of the ones really caused the issue. And then we'd figure out if it was the module that was causing the issue or some sort of a wiring issue. What happens if we can't start a session with a scan tool? Most of our modern scan tools have an auto ID function. And the way that they automatically ID the vehicle is they talk to the PCM and say, give me your VIN number, and the PCM goes, oh, okay, yeah, sure, here it is. And the scan tool can then decode what vehicle it's speaking to just by the VIN number, just like how we can decode what vehicles we're messing with the VIN number. It knows model year, manufacturer, place of manufacturer, is it even four-wheel drive, what size engine's in it, all kinds of information. So if that doesn't work with a Snap-on scan tool, we're pretty lucky because we can just go in usually by make, model, year, and that's kind of like a backdoor in there for us. With some other scan tools, it won't give you that option. You have to like try to communicate with it. It'll say failure a couple of times, and then it'll give you the opportunity to enter the part number for the PCM or the tear tag / calibration number. So on like let's say like a Honda vehicle, every sedan from 2010 to 2015 has the same PCM in it. They just have different programmings in it. So that's basically what this tear tag information does. It's like, okay, we'll give you enough information that you can talk, but you're not going to be able to do everything right now. Then when we get into there, we can do what's called a network test, and it's just roll call for all the networks. It'd be like ABS module, present, body control module, present, audio control module, present. And as soon as it asks for one of the asks for a module and it doesn't respond, it notes that. And if a module that does respond says present, and also I haven't been able to hear from this guy from a while, it's going to note that as well. So it will help us in our diagnostic process. At least we can use the scan tool in that case. A last look at our fancy modern communication network. And then a very, very quick look at LIN networks. LIN networks are newer. Well, they're also older, but they're coming back onto the scene, so let's just call them newer. So these are one-wire networks that work between two modules. There's like a master module and then a receiver module. The master module, like this master control switch, this just sends out information saying, hey, the guy pushed the driver window down button, or the guy pushed the driver window auto down button, and it just sends that information to the driver's door module. The driver's door module does not respond, doesn't send any information back to the switch. It just receives more than just a simple voltage change. It sees like a little Morse code that is giving it a little bit more information, seeing as one-touch windows are becoming really popular. Then it can either control its directly wired output. So in this case, if I wanted to roll down the driver's window, it would just control current flow through the motor in the correct direction, right? Whether it's going up or going down. Reverses polarity, so it controls that. Or if we need to control another motor, window motor in this vehicle, there's a LIN that goes to another door module that's hardwired to that motor. So these LINs are just single direction. They don't go back and forth. It's just a way to send out a little bit more complicated information. Versus an MSCAN, where the driver's door module and the passenger door module can actually talk back and forth in that case, which is more convenient for sure, but more expensive. So it's just walking that fine line between functionality and cost, basically. All right, and with that, we end our lecture.